All right, so anyway, hi, I'm Joshua Krage. I work for the chief engineer for NASA. In the office of the chief engineer, my role is to basically keep the chief engineer out of trouble. Really, I've got several different areas that kind of all overlap. I kind of describing three big areas: space sustainability, or making sure that, and the subset for my area is the technical guidance for making sure an active spacecraft is not going to hit something else, like another spacecraft, a debris object, or anything else in orbit or in space. Something we call space protection, which is focused on making sure our spacecraft are adequately protected from adversarial threat. And our newer area to try and integrate things more effectively through our engineering process that we're calling system security engineering. The National Institute of Standards and Technology is calling it more trustworthy computing. Multiple U.S. government agencies now are aligning around the term of system security engineering, which is really just the art and future discipline of, while we are working through a formal engineering process, we're bringing in the security concerns and basically building what we need from a security outcome into the process. So we're looking at the old adage of don't bolt it on, just build it in. That's what we're trying to accomplish. So NASA relies very heavily on our engineering process to accomplish all of our complex missions. So we have a variety of engineering disciplines. Heard a couple of talks earlier this morning from our software assurance side, from some of our more electronics and engineering capabilities, testing capabilities, other fun things like that. So almost every engineering discipline you can think of has some application in something like NASA, even some more esoteric areas. It just varies, how many we need, how esoteric the discipline gets. We also have a discipline called systems engineering, which is really kind of our secret sauce in a lot of ways. It's the discipline of making sure that when we come up with a mission design, mission concept, what we want to accomplish, we are thinking through all the technical issues along with all the requirements, all of our costs, our schedule objectives, basically everything we have to worry about, and through a disciplined process, deliver a system that actually works, that delivers on its intended purpose. And that gives us some insight from a security perspective of what we're trying to accomplish, which is, well, first of all, we're worried about mission success. Our missions are supposed to work. NASA's job is to deliver science data to explore the boundaries of the universe, to extend the presence of humankind throughout the solar system and perhaps beyond, to help advance aerospace technologies and capabilities and keep the national aerospace safe and secure. So that takes us in a whole bunch of different areas. But we all know that the practicalities of physics, of technology, of capabilities are always limited. You ever have enough time, enough budget, enough people, right? So there's always these trades that we have to work through. We're trading off either spending more money on something so we can make it better, or accepting some less reliability in some portion of our environment to offset cost or timeliness. We make those kinds of trades all the time. But figuring out what the right trade is, or perhaps not right, but the most effective trade that we know of at this point in time, based on our current knowledge and current point in the process, that's a lot of the decision logic that we go through. In other processes, it's making risk conversations, accepting risk here rather than risk there, or in a safety conversation, I'm going to prioritize safety of my crew over the protection of the vehicle or the spacecraft over almost anything else that we're going to do. Our humans are squishy. We want to keep them intact. We want to get them back. We want to make sure they're safe when they're out in space and actually get back safely. So that drives a lot of our thinking and also drives a lot of our assumptions about how we're going to accomplish that. So more practically, going down a little level, when we're in space, what are the things we're worried about? Also, as one of my colleagues has since retired from NASA put it, we already have a gazillion things in space that are trying to make our mission break or fail. Right? There's no atmosphere. There's ionizing radiation. There's all sorts of other things that are going on out there. There's natural objects out there. We're throwing more mass into space and orbit. There are things we have to avoid. So all sorts of things can cause our system to fail just by virtue of where they're going to operate. Part of our engineering process is to account for that, but also to account for things that we don't want to add to that failure load by not designing well, by not thinking through what could go wrong. Especially when we have a very large and complex mission, it's very expensive. We want to make sure the return on investment comes out, right? So with the long design process, we iterate a lot, we challenge our assumptions, we go through execution to make sure. And we're working towards making sure that security is a consideration in that just as much as safety is already. NASA has a very strong safety culture, right? So anything that can cause a safety issue is also a security issue. If it's a security issue, it's often always a safety issue. There are cases where we're making trades between those. My go-to answer is, if you look around, typical venues like this, fire doors. If you think of it from a security perspective, a door that could be opened in one direction could be left open and therefore is a weakness in your outer perimeter of your physical boundary. That's a risk, right? Well, from a safety standpoint, we know just from studying past disasters that it makes sense to prioritize getting humans out of a dangerous facility if there's a fire or some other hazard going on. So we've made a conscious choice through our regulations to say that it's more important to save our humans and give them the opportunity to escape a dangerous situation than it is to protect that outer boundary. Now, if you're really concerned about security, then you put like a guard, a camera, or some other alarm maybe on that door and things like that. Just things you can offset the fundamental weakness there. And that's just another example of the kinds of trades we're going to go through. So also in the space environment, so I talked a little bit about conjunction assessment, or basically avoiding other space objects to prevent an impact. So if I'm in command of my spacecraft, and I know I'm coming up and a close approach from other spacecraft, one of us has to potentially maneuver to keep both spacecraft safe. If the other object is a debris object, natural hazard, that I've got to take that opportunity. If I don't have that ability to maneuver, then I got to cross my fingers and hope that we don't actually get that close. But if we bring in the adversarial perspective, what if someone were to gain control or deny me the ability to control my own spacecraft? Now I've got a problem. I'll have a security problem for me, but now I potentially ended up causing a hazard to future space operators. So if you think about this from NASA's very big on our space sustainability efforts, where we're trying to keep space basically free and open for anybody, not just the US, but anybody to use and use peacefully and productively. We have a whole line of initiatives around that. If I can't protect my system from contributing to that greater goal, create hazard that greater goal, then I may not have done a sufficient task on my end. So this is also philosophically kind of where we're approaching some of these challenges of how we have to think about the security world this year. So in addition to the ionizing radiation, I just want to quickly hit some of the other hazards that are out there. Think about temperature. Space has no insulation, right? So any heat generally kind of dissipates really fast. So we have to put heaters on some of our systems that draws power. Sometimes we cool our systems. And just we had a recent presentation where we had done some studies on cryogenic temperatures on the lunar surface. So if we want to operate things, they're going to be throw them to the moon, whether or not we have a human around them, say a lander system, a sensor package, whatever. The characteristics of the lunar surface are still learning, but kind of interesting. There's a lunar night, longer than the Earth night, right? It's days, I forget exactly the number. And in that time, your temperature goes from very hot when you're in the view of the sun to very cold. And so you're constantly swinging up and down. And it turns out those temperatures, the cold temperatures, are basically cryogenic temperatures, ultra cold. And a lot of electronics, a lot of the formulations of electronic components won't survive. They won't maintain charge in batteries. The transistor capacitors might start breaking down. Basically, as they start getting heated up, start trying to draw current, they won't work. Some formulations will, right? But this starts affecting a lot of like material choices, which will also then limit what components we can bring in or rely upon, which also then limits, what software can run on, right? So these are the kinds of things we're going to be working through as humanity goes further out from the moon and beyond. And we're going to have more surprises like that as we learn more about what works and what doesn't work. And part of our job is to make sure we understand what might not work before it presents a hazard, especially to our humans, but also to our team. We'll throw a sensor package, we'll do some testing, we'll discover more information, and we'll share that. But the priority there is to protect our humans, protect our future humans' ability to continue to explore. So that's switch to talking at the actual space systems, or eventually lunar systems or Martian system. It was hinted at by Michael's talk yesterday, where everything is over the air, basically, for typical spacecraft. If you think from a security or safety perspective, your boundary is basically the physical parameters of your spacecraft. Once I launch it, I don't have a human that's gonna go touch it. So a lot of our assumptions, especially from an enterprise IT standpoint, about how we would mitigate or recover from anomalous situations don't really apply in space. So if my system needs to be rebooted, how do I do that when I can't go physically toggle that power switch? Um, if my logic that we respond to my remote command is at risk because of a single event upset or something like that, have I thought that through and do I have some ability to recover from that state? So this is the kind of the fundamental challenge we have in thinking through space systems and how we're going to use them. So now here's the next question. All right, so if I come up with some mechanism, we can go through a variety of possibilities. Come up with some mechanism where I have some ability to send something that I'm guaranteed my spacecraft will be able to receive and then toggle that reboot for a subsystem of the entire spacecraft. What can I do to protect that from Michael trying to do the same thing when I don't want him to? That's our security question in a nutshell, right? And that's just one aspect of it. And that's not easy, and that's going to rely a lot on things like encryption or authentication. How can I make sure that I can send that command, but Michael can't? There's lots of layers we can put into the complexity of how we might design something like that. But at its fundamental core, right, what I'm trying to accomplish is I want to maintain positive control of my system. I don't want anyone else to have the same ability. How do I do that when I do not have constant communications? I do not have headline links. I have ultra high latency in most of these links. A lot of the common patterns for authentication, challenge response, OAuth, other patterns like that, they are not going to work in an Earth to space kind of environment just because time of view, latency, number of challenges, responses that you have to handle, and the amount of logic you have to handle in that process, this is not going to work. Where's your source of truth? Where's your authoritative function that you have to rely on? In the past, a lot of entities have relied entirely on protecting that command link. How I would send commanding sequences, software code, anything else to the spacecraft, and perhaps some return link. I protect that with some authentication or encryption. That's a great step, and that's a fundamental thing we have in NASA's requirements and one of the public standards that I own. That's our first one in there, protect that link. But is that enough? And as we get into the ability to use, for example, a Linux-based system, what features can we take advantage of that will be available to enable that? How much complexity do I need to introduce to the process of managing my spacecraft that will give me some of the security assurance I'm looking for at maintaining that positive control? And how do I do that without solely relying on any one layer? That's the depth of things we have to work through on some of this. So reason why we are looking at that crypto link is possibly not being sufficient is the architecture of the system is changing and how we're using that is changing. So, and also there's the potential threat of if a secret quantum computer becomes available tomorrow, thanks Google for your research, let's make Google here, new quantum chip, further threatening the state of modern cryptography. Cryptographers around the world, thank you, but no, it's a good advance. If the magic, quantum anti-crypto defeat tool becomes available tomorrow, right? And AES and other modern cryptographic algorithms are no longer safe. What do you do? And that's a hard question that we're all grappling with right now, right? There's newer algorithms, newer methods, but what other techniques can we bring to the table? What other techniques that will work in this over-the-air environment in a highly constrained compute environment are applicable there? This is a whole area that there's not a lot of good research, solid research on. We've all been doing enterprise-wide. We've all been doing a lot of research on what we'll do for post-quantum cryptography. We'll pull out this cryptography system, we'll put in a brand new one. We'll toggle the bit to associate an algorithm. We'll move to a higher key size in some cases. And we've got lots of techniques like that. That's not going to work on a space system that's already up there. That's not going to work on a space system that has a finite capacity or hardware. I can't really effectively go back and upgrade my entire compute package on my spacecraft. So what I launch with is what I'm going to be using. So the other question I use to channel people's assumptions is, so NASA's longest lasting spacecraft for the Voyagers, launched in the late 70s, still operating, left the solar system. They're old, they are experiencing their age. We are still able to keep them functional. But that puts us in the category of a 45-year program. How do you design a spacecraft or a system that's going to be operational for 50 years? And when you bring in the security threats to that, how would you start trying to figure out how to design a system that might be able to keep up with security threats that did not exist when it was launched? And also the assumption that we can't change the hardware. Maybe we'll be able to change the software. And that's an open conversation. But I think that's also an area that the Linux community may be able to help us reason through as we rethink some of our assumptions about how past spacecraft have been built in context with all the challenges and assumptions that we have to do and the determinism that we have to demonstrate. Scott's presentation this morning talked a lot about the assurance cases that we have to build. How do we do that for a mission that's going to be out there with a 50-year-old piece of hardware? But maybe we can do something in the software. A lot of the other factor in this is that the economics of space have changed and are changing. So it used to be that space systems were only affordable by government, by national entities, right? Kind of why NASA still exists. But the technology basis for space systems has dramatically improved. We have more capable technology. It is cheaper. Launch costs have come way down. So if you have a few $1 million in the back pocket, burning a hole there, right? You can get a spacecraft into orbit. It might last for a couple of years, depending on what you did with it. Probably not going to be one that you send to Mars or anything beyond that, so it won't survive that long. But you can afford it now, right? It's in the realm of even a small business in some cases. So we are shifting from these very large, very complex 20-year missions to smaller, more nimble things. Perhaps 10 spacecraft do the function of one big one in the past and be more resilient and capable. We're seeing the economic curve on that really come down, really improve. The components we can buy, right? They are more readily available. The quality and the rating of those components is generally better, maybe not sufficient in all cases for space. This is the last presentation showed. But we can do more with it. Some entities have demonstrated limited success, limited in terms of time, months or years ago. Just taking off-the-shelf commercial IT products and tossing into space. Now, for all the reasons you saw in the ionizing radiation discussion, right? You expect they're not going to last for that long. But so I wouldn't depend on them to get maybe your weather or your data relay, like a Starlink type thing. But it might be good to demonstrate your capability, test some functionality just to see what you can accomplish. Yes, sir.
You're covered a lot of really deep stuff here. And if you think about NASA's track record of decades of safety, NASA, I would say, knows how to do that. And you use the analogy of the FAA 178. NASA's got a lot of research, a lot of guidelines. You've seen some of that in previous presentations. How does this flow down into this commercial space world and then to other countries? And then there's different levels, right? Like the Dream Chaser that Sierra Space builds, that goes back and forth to space, it glides in FAA airspace, or maybe DO 178 requirements for that. There's low, orbit satellites that are unmanned, and then you have other things out there like what you just talked about. The mean time between failures, if something goes dark in 2 years and crashes into the International Space Station, that's a pretty big problem. Is there there's best practices and guidelines from NASA? How do you see that flowing into this commercial space world? Are there requirements or guidelines, and how do you see it?
Yeah, I am going to get to some of that.
Okay.
But in general, anything we know that we are not prevented from sharing due to a legal requirement, proprietary data or something along that line, we work to share. So like one of the questions I often get is, are we worried about our science spacecraft and the science data, people watching what we're sending or what we're doing in space? And the answer from our science side is no, because like the picture on the back from Landsat, that's actually USGS's picture, that's not NASA's, but all of our data we share. So from a science perspective, for the science community, right, almost, it's almost as simple as saying that everything we detect is shared. Practically, it's not technically true, just because a lot of metadata, other things like that are not important. But, fundamental products from our space sensors are just shared worldwide. You download, terabytes and petabytes of data today. And we are sharing that data in other ways, other areas as well. So that's just the science aspect. We also share a lot of our research data. Again, we're restricted in some areas from like export control requirements and things like that, where it's legal frameworks for doing pieces like that. But if we create a piece of technology, one of our core responsibilities as a civil space agency, as NASA, as opposed to our other space partners like the NOAA or USGS, one of our responsibilities is to commercialize that. So if we come up with an invention or new or advanced capability, we're always looking for a commercialization partner. So we have a very large technology office that tries to identify a partner that is interested in licensing or partnering with us on commercializing that technology. So a lot of stuff we've done in the past has emerged in, we have a whole impact report on a regular basis that comes out, so a lot of that is there as well. But at a discipline level, like where I'm talking about from a security or engineering perspective, that's a little harder because that starts getting into organizational culture, approach, philosophy, and technique. And that ties very much to what is the business. So like what Boeing needs for what Sierra needs, Sierra Space needs versus Rocket Lab or SpaceX. Are a little different.
Yeah, I wouldn't say that. I would say it has to do with the hazard model for the environment working. The flying public will not consent to the same level of hazard that an astronaut will consent to. Therefore, either we find a way to lower the hazards so that the public will consent to that, or we don't fly. If astronauts require the same level of reliability that we have in civil airspace, they would not fly into space. It just wouldn't be cost effective.
How do you define that level? Like,
Yeah.
FAA is DO 178, right? Or slower things you see at the.
Soft leveling. And it has to do with some safety and security. I don't want to digest.
Yeah.
Safety and security are negative requirements. You can never make a system safe. You can never make a system secure. But it has to be a forward ratcheting thing where you can't go backwards. So the greater degree of rigor you find you need to assess the situation, the more you know about the hazards and threats, those become parts of your thinking factoring forward into your next design.
What, like NASA's done a great job. I mean, the space shuttle disaster 40 years ago, or whatever it was, taught NASA a lot, right? There's a lot of lessons learned from that. A lot of that has manifested itself in how NASA builds safety into your vehicles. How does that flow into other companies?
Yeah, that's what's good. That's why I spent a little time about our philosophy up front was we could agree at that level, there's noble goals there, and in different organizational entities, they will often articulate similar goals or the same goals in some cases. But when you get down to that next level, how you apply them within the business environment or the organization's business process environment, that's where the application of the discipline becomes a challenge. We might be working from similar models or similar goals, but it's back to that application and that translation. So Scott showed this morning our software engineering requirements, right? Some of our suites. And they're very robust in a lot of ways, and they're very rigorous, and they're written from a certain point of view, and they're written from a variety of layered assumptions that we've accrued over the years. And we try to explain, or at least ourselves, and attach to our requirements, we try to explain what those assumptions are and how we should think about applying that requirement. Communicating that to a different business organizational entity is often challenging. We can all agree, we can pull up our CAD or slide rules or our tools, right? At the tool level, we might agree, oh yeah, this input yields that output, this process that does this, we're using center tools. How we use those tools, how we use those tools to address those hazard models, those requirement models, that is where it's a bit more challenging. We've also learned that what some industries might consider sufficient from an analytical perspective, because we tend to be coming at it at our safety disasters in the past and our culture of trying to understand the deepest possible level how something might work. Our level of discipline, of depth we might push to understand some anomaly or hazard or consequence might be different than another operator might consider, right? So back to what's safe for you, is that safe for me? Do we have a common understanding of that? we might think we do, but until you get down to some of our words are, if we can build like from a first principles, from a physics and engineering first principles basis to explain why something happened, that we have some confidence that we can work with it. If you are making decisions but don't have that understanding, are you truly understanding the hazards and the risks and the associated risks? And that takes time, and that takes money, that takes experience, it takes a whole lot of stuff. So again, things we know affect us in space that challenge our past assumptions of what's possible versus taking a data center methodology and trying to put that in orbit, right? You've now seen enough from just today, right, that there's some assumptions that have to be assessed. But if you bring them in, at a deeper layer over more areas of effort, then that's where you start getting these. Are we really talking the same thing? Are we really having the same fundamental understanding? Or are we, at different levels of the conversation? And that's where that mapping is challenging. That's what I was trying to get to is we can talk a lot about it, we can explain, but it's not a simple conversation. It's not just do this. There's no silver bullet in a lot of this. It's a repeatable process of doing it. Yes.
So just saying the same thing in the same vein. So if the challenge is to transferring this mindset kind of a process methodology to the, let's say, to the further commercialization is the problem. But you still have a way to teach young engineers hardware, software, who actually coming and joining NASA today. So, because otherwise the organization would not be able to perpetuate yourself, right? So there is a process that exists today that allows you to upskill people like college grads who come and join work for NASA, build out the systems of the future. Are this process is transferable in some way, shape, or form, or only can happen only inside NASA?
I'm not suggesting this is a NASA unique thing. We have a lot of knowledge. It's just not a simple matter of just, writing it down and trying to transfer that, right? So the mentorship model, we have a very robust internship program. They're very focused on all the traditional STEM career paths, not exclusively, but very, very STEM focused. Here at Goddard in the summer, we used to get over 1,000 high school to college and graduate level students coming in some level of internship. So that is one of the methods we have to both recruit and to share and to train. If a commercial company wanting to operate in space wants to try and partner with NASA, we have a lot of engagements to also make that possible. There's a challenge sometimes where a commercial vendor might not appreciate NASA if we're in a contractual relationship where we have some oversight responsibilities because we are funding or own some accountability for it. But we have been successful in a number of cases with many of our partners where we've been able to work at a technical level to explain again what our assumptions are, how we approach the same problem they may be experiencing, and work with them to find a solution. And that's increasingly critical to us as NASA is shifting from a lot of very in-house controlled systems that we fully own the outcome of. So if we're in a contract relationship, we'll tell you what you need to do or what you need to deliver, to this new, more partner-centric perspective and commercial partner perspective. So if you look at some of our public strategies and our Moon to Mars architecture, we've already articulated when we go back to the moon, it's not NASA by itself. It's not NASA and US companies by itself. It's going to be NASA with international partnership and commercial partnership. And so that's another piece of this is we are making sure we are able to share a lot of it as we can, but it requires that sustained engagement.
Yeah.
Right. It's not an artifact-based delivery.
Yeah, it's like in commercial space, like that will be like a dojo style type of.
It could be, yeah.
Principles, because large organizations have the similar problems, albeit like on a different scale, but they essentially try to solve the similar use cases.
Yeah, so one other subtlety is we're not really, as a government agency, we're not a training organization for other customers. But we are a partner support function in the technology and commercialization or basic technology space and aerospace capabilities. So slight things in there. It'd be kind of interesting to explore some of those other options. So on the spacecraft or space vehicle, we have a variety of subsystems. So this is why our safety and engineering processes are kind of very broad and very integrated or very holistic, I should say. See, a typical spacecraft has a bunch of capabilities that all have to work for that spacecraft to survive over time. Just basic Earth orbit stuff that we've been doing for 50 plus years now require things like attitude control. Like as you orbit around, can you maintain your attitude, especially if you're trying to stare at the Earth and take pictures or sense? Are you able to keep up with the rotation as you move along? You get a cruise from orbital momentum you got to dump. So basically, there's a whole complex orbit sustainment, orbit maintenance, momentum management, attitude control. All those things have to be handled. Well, from a hazard perspective, if those don't work, then I may be creating a hazard not just for my spacecraft, that may be inoperable. I may be creating a hazard for someone else's spacecraft. These are goals we do not want to have happen. Power subsystems akin to like batteries and laptops with big, huge solar panels, a lot of dynamics in there. We use a lot of GPS receivers for position and navigation support as well as timing. Timing is immensely critical to all of our space systems, especially when you're trying to change your orbit or know where you are in space. So all these things have to work, and they're all have discrete logic. And it's not as simple in all cases as like a daughter board, main board relationship. They are independent logic sharing information between multiple components on the system. Right. So it's also not as simple as saying it's a network system. Right. Very few spacecraft I know of today would be viewable as a network in the classic, Internet of Things kind of perspective. But there are similarities. There are things we can reason through in some of those cases. I'm familiar with like bus technologies like CAN bus, FireWire, USB. Those technologies are largely at play, different variations. Some older, some will shift it a little bit. And we are moving from as the new technology comes out, we are moving from a lot of the more legacy capabilities into things like time-sensitive networking on Ethernet, TSN Ethernet. That's going to be one of the big areas that I think we'll see a lot of engagement off for future space systems. So we control all of that through some central logic. Historically, we've had a very one CPU that because of radiation hazards, other rating hazards, was made physically large, but basically just one CPU and relatively low clock rates, and laughable to like even modern watches and phones, finite capacity of RAM. And recently, we've had the ability to get to maybe 2-core systems, some of the ARM chipsets and the VGA applications. Most of the time, those multi-cores are actually implemented like a lockstep mode, where those CPUs are running the same commands in parallel. And if one has a failure, the other one is still going and it can be recovered and you can get back into sync. So it's really just one functional CPU set of instructions operating in parallel. Some of the upcoming hardware that NASA will be using and other commercial entities are likely to use are moving into a multi-core environment, right? So, and with advances in multi-core, with RAM access, some of the chip architectures, and virtualization, we can expect that we're not going to use, say, 8 cores just for our flight avionics or flight software. We might be using 1 or 2 cores for that, but we still have lots of other cores that are available for additional capabilities. So because we've been limited in the past to 1 CPU to run everything, so that's all the inherent spacecraft safety and health functions, how I'm communicating to and from the Earth, how I'm maintaining my attitude, maintaining my power, all those fun capabilities in there. But also whatever the purpose of that spacecraft is, the instruments, the payloads, the functionality that we do. In the past, we've been limited in compute resources. We wanted to optimize. So we've integrated the instrument with the flight software, all running on the same CPU within the same memory domain. From a security standpoint, that is not optimal because any flaw in one area could affect somebody else. So with the new architecture, right, both software, but also at the hardware level, right, where we can start separating these out, we're having to rethink some of our design assumptions. So rather than efficiently designing my instrument, all my safety and health stuff is run from the same real-time operating system on the same CPU using the same memory. Now I'm separating that out. From a security standpoint, I want this. From a safety standpoint, I probably want this. asterisk there. Because I've just introduced complexity, right? But if I can separate out the fault tolerance failure domain, the security management domain, if I can separate out what I need for my basic safety and health and my command and control from what my payloads or instruments need. And I can keep the safety aspects separated, now I've got a lot more opportunity. So maybe now my payload doesn't have to be as safe as we've required in the past, when it was more tightly integrated and do something that posed a proximate hazard to it. From a security standpoint, I want this, right? So the hardware capabilities are coming on board. So back up before I get that part. One of the other trends in the CPUs that may have escaped awareness, I'm just gonna bring it up for explicitness, is you may note that all the CPUs that I've talked about in the past have all been more RISC-based or reduced instruction set architectures and not complex instruction set. So we're not talking Intel and AMD. We're talking PowerPC and Spark. Those are the two architectures we've used primarily in most space systems in the past. A lot of commercial systems are now using basically what's an ARM architecture. And most of those, not all of those, but most of those are likely to put on an FPGA, like a Xilinx or some similar system, whereas the FPGA is emulating CPU core. But these are all, smaller instruction set, not the complex instruction set of Intel and AMD. So we're having to shift it. The next generation hardware, I'll talk to you about what one of those examples is following one line is following on the Spark architecture, and the other one is going down the RISC-V architecture. Right, they're all very different instruction sets, right? And we don't always have library or perhaps even kernel support in some cases. And certainly not all the functionality may be there yet. So we have to think through what the implications of that are from a software standpoint, software support standpoint. Most modern CPUs on the Earth world, right, have some security features on the board. Maybe not part of the CPU, sometimes yes, sometimes no. So looking at features like secure boot, TPM modules and things related to that. We won't have necessarily a TPM like architecture in space, but maybe we need some secure boot thinking in those areas. How will we interact with software with that hardware? ARM has ARM has a security feature set to control access to memory locations. I wrote down the name of the feature. Yeah, sure. So thank you. Yes. Yeah, great. The RISC-V world has WorldGuard that Microchip developed. These are hardware enabled controls within the architecture of the CPU, the memory access. That I think has some security value. A lot of boards have some kind of security controller, TPM or something similar, or a system management controller, control like battery and firmware updates, a variety of things like that. What we are putting into control of the hardware, basically like the kernel or something in that sphere, needs to be able to interact and support all that. I don't want to launch hardware and security features at the hardware level that I can't use in my software. I need to have my software support that. I need to have that lovely interaction between the two in order for me to accomplish my objectives of protecting my system from external hazards and from internal hazards as well. So one of the CPU changes that is about to land and become available. NASA has worked with a commercial partner called Microchip, big microcontroller provider. And so we've developed a thing called the high performance space computer, the HPSC. So Microchip's partners like PIC 64-HPSC. It's all on their website. We've been working with them for a long time on there. It's a lovely shared partnership. But basically, we're going from legacy 1 core type architectures to a RISC-V based. It's got 10 cores on the board. 8 of them are available for applications. It's got a system management controller, security controller, TSN Ethernet bridge, all on the SoC that's coming out. I think the timeline is we're seeing lab grade boards come out now-ish. The boards rated for radiation tolerant and radiation hardening. They've got 3 lab tolerant and hardened versions. The tolerant and hardened ones are the ones we can use in space. Those I think are expected to be coming out in about another year from some of their partners. But
dovetail off.
yes, sir.
I noticed, it's part of the PIC 64 line. So now NASA investments is also being used in automotive and industrial.
Yeah. So, yeah, a lot of the embedded system, community is moving into the cyber architecture fast.
Yeah. It also has, I think, more AI engines on it, or vector processors. Like, what do you-
I don't think the PIC64 does, but a lot of the hardware instruction set, the RISC-V feature sets that are used, part of what our criteria or goals were was to enable some of the AI ML capabilities. So a lot of the vector processing functions and extensions in the RISC-V feature set, the specific cores that Microchip is bringing to the HPSC include that. And these are, I think it's like the Sci-Fi 850, I have to go back and double check the spec sheet, but it's something in that space. It's all the Sci-Fi core. One of the more advanced ones. But when I first heard about it and started poking at it from, what will this bring to us from a technology capability, security opportunity capability? While it wasn't necessarily an inherent NASA requirement, Microchip was bringing it to the table as part of their contribution to the concept, ticking off all these little objectives. So I'm very much looking forward to using that forward in real operations. Once we actually get software to work on it. Rich. He's working on some of that, so.
I assume it's gonna come with Linux all pre-installed.
It could. There's no reason that, the team that was working with Microchip on it, they, have a lot of the, core libraries and functionality already tested and evaluated. So, yeah, they've done a lot of work to make sure everything's ready for it. So now it's just a matter of, getting the boards into developers' hands, into lab hands to test these things out.
Putting the BSPs together as well.
We get all the integration layers we need, yeah, all the layers.
Yeah.
One area that we've been looking at, and some of our, government partners have been looking at is, protecting, the onboard memory. The memory attacks are a huge deal. Whether you're a Rust aficionado or say the C++ can solve the same problem, I'll let those who are a little closer to the argument to debate that one. But there's lots of discussion on it. But fundamentally, right, we're all concerned that security vulnerabilities can be expressed and exploited through memory safety flaws. One of the things I like about the WorldGuard feature of the RISC-V set is there's some opportunity there to perhaps that testing required, maybe some operational experience on it, but we could shard off, mask out whole areas of memory. So I can fully separate at a hardware enforcement layer with some configuration at the board level, my software cores from all my other cores. Right, so if I can do those things in the trusted for an ARM chip or WorldGuard for an RISC-V chip or any other similar architecture, and that's supported by how I design the system and how the software runs within those containers. That's already, I have a greater security assurance, because I've segmented my architecture out a little bit. I also have some separation of my safety, failure zones and things like that. So again, looking for a lot of improvements in that area. So, last piece I wanted to cover was, in all of this, what we're shifting from, or trying to shift from, especially from a government and oversight perspective, and from a system security engineering perspective, is getting out of this thou shalt and compliance approach and building what we're calling assurance cases, whether it's a safety assurance or security assurance. What evidence can you bring to the table that demonstrates that your system has some quality of safety, some quality of security? And what are the relevant gaps or hazards or challenges and opportunities they have in those domains? So if we express that at a software level, at a kernel level, at a subsystem level, at a flight software level, at a system level, now we've got a lot greater assurance that we understand what's happening, answer some of the determinism questions Scott was raising and others have raised, and we can have some confidence that what we built matches our goals and will function as we think and envision to work. There's always going to be some ringer that will hit us operationally somewhere down the road. Well, we can't solve problems we don't yet know exist, but we can build the basics to allow us to respond to those unexpected problems. So that's where I hope we can all work.
Thank you.